right, so lesson 58 is on sequences and series. So we spent a lot of time on this in Algebra 2, so we're going to review some of these concepts today. So number one, it says find the first four terms of this sequence. So this is called an explicit formula. I know the word explicit makes you think like explicit material on a CD or something. It's not like that. So explicit means it's just where you can plug in the number. So if I want to find the first term, I get 4 times 1 minus 3. You guys don't even have CDs anymore. That's funny. On iTunes. So if I plug in 2, I have 4 times 2 minus 3, which is 8 minus 3, so we get 5. If I plug in 3, I get 4 times 3 minus 3, which is 12 minus 3, so it's 9. And if I plug in 4, I get 4 times 4 minus 3, which is 13. So the first four terms of the sequence would be 1, 5, 9, and 13. Okay, so they could be more complicated. We could have things that have, exponents and so on. So if I want the first term, I find A1. A subscript 1 means the first term of the sequence. Sometimes we have sequences that start with 0, especially if it has something to do with time, like time 0. So we have 5 plus 2 times 1, and then negative 1 to the 1. So we're going to get 5 plus, so we do our exponent first, so negative 1 to the 1 is negative 1, times 2 times 1 is negative 2. So we're going to have 5 plus negative 2, which is 3. Then we find a subscript 2. So we have 5 plus 2 times 2 times negative 1 to the 2. So I have negative 1 squared is 1, times 2 is 4. So I have 5 plus 4, which is 9. A3 is 5 plus 2 times 3 times negative 1 cubed. So the negative 1 cubed is negative 1. Times 2 times 3 is going to be 6 times negative 1 is negative 6. So I get 5 plus a negative 6, which is negative 1. And then the fourth term is 5, 2 times 4, negative 1 to the 4. So negative 1 to the 4 is 1, so this becomes 5 plus 8, which is 13. Okay. And from there on, it will alternate, meaning it will go from positive to negative to positive to negative to positive to negative. But the first couple terms were positive in this case. Does that make sense? Okay. So this next one is what we call a recursive sequence. You guys remember these? So this is where, like, for instance, the nth term, see how that would be the nth term, is based on the term directly before it. So see how the next one is a sub n minus 1. So for instance, if I want like the 100th term, I have to use the 99th term in order to find it. So if I'm trying to get to the 100th term, if I'm using a recursive sequence, I have to find the first, the second, and the third all the way to the 99th term before I can find the 100th. Yeah. Very annoying, right? So here's what we're going to do. So if I want, so I already have the first term. Do you guys see how that's 1? You always have to start with a certain term. So if I want a subscript 2, what this means is that I have 3 plus 8 times, what subscript will this next part have? Yeah, so it'll be 3 plus a times a1. Because basically I'm plugging in n equals 2, and so the other one's going to be n minus 1, which is going to be 2 minus 1, which is 1. But what was a1? 1. It's not always 1. Don't assume it's 1. So I get 3 plus 8 times 1, which is 11. So now I want to find a3. Well, a3 is going to be 3 plus 8 times a2. And what was a2? 11, right? So we have 3 plus 88, so we get 91. Makes sense? And then a subscript 4 is going to be 3 plus 8 times a3. Well, a3 was 91. So we have 91 times 8, and then we add 3 to it, so we get 731. Okay, so our 4 terms there were 1, 11, 91, and 731. Make sense? All right, so if we have something that says find the 20th term, we're fingers crossed that this is not a recursive sequence, that this is an explicit one. Is this one an explicit sequence? Yeah, so if I want to find the 20th term, we're very lucky. All we do is we plug in 20. So 2 times 20 plus 7 ends up being 47. Okay, so we can have lots of sequences. So they can be what we call arithmetic or geometric, or they could look like this, where there doesn't seem to be like a certain pattern. Like I think C, like it would be hard to figure out like what that pattern is, right? Okay, so we're also going to talk about factorials. So factorials are going to be used with probability type stuff. So if I have 8 factorial, do you guys remember what that means? Yeah, 8 times 7 times 6 times 5, all the way down. So basically we would have 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 all over 5 times 4 times 3 times 2 times 1. Okay, so what happens is I could put this in my calculator, like there is a factorial button. Do you guys remember how to find the factorial button? Okay, so on your calculator, so pull that out. You can hit 8, and then you can hit math. Go over to PRB, and it's option 4. And then you can divide by 5, math, PRB, option 4, and you would get an answer. Okay, but a lot of times I put these on the non-calculator test because I want you to know what it means instead of just plugging things in. Okay? So what this means is that the 5, 4, 3, 2, 1 can be divided on the top and bottom. It's like reducing fractions. I'm dividing by 5, dividing by 5, dividing by 4, dividing by 4, right? So I end up getting 8 times 7 times 6, which is that number that we had. So 336. So when I see something like 12 factorial over 3 factorial, 10 factorial, I don't want to write all that out. So the way I typically write it is I would do like 12 times 11, and then I'd say, oh, I have 10 factorial on the bottom. So I stop at 10 factorial. Does it make sense? Because it's 12 times 11 times 10 times 9 going all the way down. And then the 3 factorial is 3 times 2 times 1. You can leave off the 1 if you want. So what happens is the 10 factorial goes away. Hey, how are you? Come on in. Oh, Brooke, you need this too. And the 3, 2, and 1 reduce out with the 12 and 11, right? So we're reducing the 3 and reducing the 12, and I'm putting like 4. Well, 4 and 2 reduced to 2. So I end up getting 22. Did you guys see it? All right, so really think about this one. Anybody have any guesses? So n factorial over n minus 2 factorial. No? Yeah. Think about with numbers. So if I had n was 100, this would be like 100 factorial over what? 98 factorial, right? If n was 100. What would happen there? We'd get the first number, 100. We'd get the second number, 99. But then the 98 factorial ends up going away with the 98 factorial. Does that make sense? Does that always happen? So if I plugged in n is equal to 7. 7 factorial over 5 factorial. 7 times 6, right? So what does that mean? So if I have n factorial, it starts out with n, and then it has 1 less than that, and then it's 1 less than that, all the way down to 1. And then I have that n minus 2 factorial on the bottom as well. So those n minus 2 factorials go away. So we end up getting n times n minus 1, which you could write as n squared minus n. So let's see if that works. So on this 100 example, I said, oh, my 98s are going to cancel. I have 100 times 99. That ends up being 9,900. If you plug in 100 for n, you get n squared minus n. 100 squared, right, is going to be 10,000 minus 100. Did you get 9,900? Yeah. Does that make sense? Even with 7, you would have 7 times 6 left. Well, that's 42. Is that 7 squared, which is 49, minus 7? Yeah, it works out. Does that make sense? Okay, so how about these sigma things? You guys remember sigma? You guys just get scared because it's a different symbol. You know how to do this. So sigma means sum. So what we do on these ones is we plug in 2 first, and then we continue to plug in every number, every integer, I guess I should say, up to the last one, this 5. So I'm going to plug in 2, 3, 4, and 5. I'm going to find all of those results, and then I'm going to add them all together. So let's do it. So if I plug in 2, I get that number. If I plug in 3, I get this number. If I plug in 4, I get this number. And if I plug in 5, I get this number. So you don't have to write it out that way. Like you could easily say, oh, if I plug in 2, I have 4 minus 3, which is 1. If I plug in 3, I get 6 minus 3, which is 3. If I plug in 4, I get 8 minus 3, which is 5. And if I plug in 5, I get 10 minus 3, which is 7. So 8 plus 8 is 16. So our answer is 16. Make sense? All right, so the next one says find the sum of all those quantities, like starting with 0 going to 3. Do you guys remember 0 factorial? You want to say it's 0, but it's not. It actually ends up being 1. 1 factorial is also 1. But yeah, 0 factorial has to be something. It comes from our permutations and combinations, which we'll talk about in a couple sections. Do you guys remember permutations and combinations? Like how many ways can 8 runners place if there are 3 trophies that are given, right? All that stuff. All right, so the first one, so we have 0 factorial minus 1. Then we're going to have 1 factorial minus 1. We're going to have 2 factorial minus 1. And we're going to stop with 3 factorial minus 1. So 0 factorial I said was 1, so 1 minus 1 is 0. 1 factorial is also 1, so 1 minus 1 is 0. What's 2 factorial? 2, so 2 minus 1 is 1. 3 factorial? 6. 6 minus 1 is 5. So we end up getting a total of 6. Is it all coming back to you? Somewhat. All right, so this says determine whether or not the sequence 7, 3, negative 1, negative 5, negative 9 is arithmetic. Okay, so if something's, did I skip something? I skipped a bunch. Maybe I can get on here. Oh, here it is, okay. So it says for the series, I equals 1 to infinity, 3 over 10 to the I. Find the fourth partial sum and the infinite sum. Okay, so we did these last year. So if I plug in 1, I'm going to have 3 to the 3 over 10, right? 10 to the 1 is 10. If I plug in 10, or 2, I get 10 to the 2, which is 100. If I plug in 3, I get 1,000 on the bottom. And if I plug in 4, I get 10,000 on the bottom. You guys all know that trick, right? If you have 10 to the 4th, it's 1 with 4 zeros, right? Okay. So this would be the fourth partial sum. So we write this as S subscript 4. It's the sum of the first 4 terms. And it looks a little bit weird. But if you write it as a decimal, it makes more sense. So we would have 0.3, right, 3/10. The next one is 3/100. So as a decimal, we read that as 0.03, right, 3/100 is how we read it. The next one is 3,000, so 0.003. And the last one is 0.0003. So if I have all of those and I line them up, you don't have to do this, but if I'm lining them up like this, do you see what we get? Yeah, we get 0.3333. That's the fourth partial sum. What do we think the infinite sum would be? 0.3 repeating, exactly. So S, which means infinite sum, would be 0.3 repeating, or you could write it as 1/3. Okay, so an arithmetic sequence is a sequence whose consecutive terms have a common difference. So an example would be like 1, 4, 7, 10, 13. The common difference is 3. Basically, we're saying we add 3 each time. I always have students ask, like, why is it called the difference if you're adding 3, adding 3, adding 3? It's because if you take any term, like if I take 10, and I subtract out the term before it, 7, do you guys see how 10 minus 7 is going to be 3? That's where it comes from. Okay, so 7 minus 4 is 3, 4 minus 1 is 3. That's the common difference. So it says determine whether or not the sequence is arithmetic. If it is, find the common difference. So is there this number that we're adding or subtracting every single time? So let's see. Yeah, so I would subtract 4. Do I subtract 4 here? Yep, looks like I subtract 4 every single time. So yes, it's arithmetic. The common difference is negative 4. Because we're saying add negative 4 to get to the next one. Do you see how any term minus the term before it is negative 4? Okay, so number 2 says find a formula for the nth term of an arithmetic sequence whose common difference is 2 and whose first term is 7. So this is tricky. I talked about swoops before. Do you guys remember when I talked about swoops? So if I have 7 and my common difference is 2, what's my next term? 9. My next one would be 11, 13, 15, right? Okay, so if I want the nth term, I think about where I start, and then each time I'm adding 2. So for instance, if I want to get to the third term, how many times did I add 2? Twice, right? In other words, I'm going from the first term to the third term. Do you see these numbers? 1 to 3. I have to add 2 swoops to get there. Does that make sense? If I started with the 11th term and I wanted to get to the 25th term, how many times would I add swoops? 14. Does that make sense? Do you guys see it? 11 to 21, or 25. 25 minus 11 is 14. So if I want to get to the nth term, I start with my first number, and I add this common difference, which is 2, n minus 1 times. Okay, I know that's confusing because you guys are like, wait, what's the n minus 1? Where did that come from? If I'm starting with term 1, and I want to get to like the 100th term, what did I do to these numbers? I needed 99 swoops to get to the 100th term. Does that make sense? It's because we're starting with term 1. Some schools teach it where you start with term 0. They call it 0. All right, that's kind of weird. I think you guys can understand this. It's not that bad. Okay, so that's what we have. So a sub n is equal to 7 plus 2 times n minus 1. And if we simplify it, we get 7 times 2n minus 2, which means a sub n is equal to 2n plus 5. Okay, let's test it. So how many terms do I have right here? I have 5 terms, right? 1, 2, 3, 4, 5. So if I wanted to find the 5th term, can I plug in 5 and get 15? Yeah, if I plug in 5, I have 2 times 5 is 10, plus 5 is 15. So it works. Does it work for a term 4? Yeah. 8 plus 5 is 13, right? Does that make sense? All right, so there is a formula. So it says the nth term of an arithmetic sequence has the form a sub n is equal to a1 plus n minus 1 times d. So as I just said, it's better to not memorize this formula. Instead, know how to get from any 2 numbers in the sequence. So for instance, if you have the 7th and the 22nd term, you have to say, oh, if I start with the 7th term and I want to add common differences to get to the 22nd term, I would need to say my 22nd term is going to be my 7th term plus 15 swoops, right? 15 common differences in order to get to the 22nd. Do you guys understand that? So if you can relate any two numbers in the sequence that you're given, you're fine. Okay? I think so many people try to just memorize the formula and they're like, oh, but I don't have A1. And then they just leave the problem blank. Don't do that. Okay, so it says find the 6th term of the arithmetic sequence that begins with 15 and 12. So this would not be hard to list out. So you could be like, okay, 15, 12. I keep subtracting 3. Do you guys see how we're subtracting 3? And so you could say, oh, it's going to be 9, and then it's going to be 6, and it's going to be 3. And so then the 6th term is going to be 0, right? Does that make sense? Okay, a lot of students choose to do that. That's fine. That's a very Algebra 1 method, though, because now that you're in pre-calc, I'm going to ask you things like, what's the 10,000th term? And if you're just listing them out that way, it's going to take a really long time. Probably the whole test, if not more, to write out 10,000 terms. right? So we need to know how to use these formulas. So if we're trying to set it up with a formula, we can say, oh, my A1 is equal to 15 and my A2 is equal to 12. So if I'm relating A1 to A2, I'm like, oh, if I want to get A2, I start with A1 and add 1 common difference, right? So I'm going to have 12 is equal to 15 plus D. So I end up getting D is equal to -3. Then once you have D, you can get whatever you want. So if you want the 6th term, you could start with the 1st term or the 2nd term or the 3rd term, whatever term you want to start with. So let's say I start with the 1st term. I would need 5 swoops to get there, 5 common differences. So I'd have A1 is 15 plus 5 times -3. Do you guys see how we get 0? Okay, so that's how we're going to do it. We're going to do it with these subscripts, like A sub 1, A sub 2. Okay, so let's try some more. So the 5th term of an arithmetic sequence is 190. The 10th term is 115. Find the 1st term. So A sub 5 is 190. A sub 10 is 115. So I realize that it says find the 1st term, but I don't want to use the 1st term yet. It's kind of like a 2-part problem, right? I want to write an equation that relates the 2 that I was given. So how do I write an equation that relates the 5th term and the 10th term? They're so quiet today. All of my talkers are taking an AP test today. So A sub 10 is equal to A sub 5 plus, how many swoops? 5. 5 common differences, right? Do you guys see how we relate them? Now some people were saying, oh, do you always put the big subscript on the left? I personally do. I kind of keep it consistent. But if you had done A sub 5 is equal to A sub 10, you could do that. You would subtract 5 common differences. Exactly. Does that make sense? Do you guys see it? You're saying, oh, I'm on the 10th term. I want to go backwards. It's up to you. I personally try to keep it consistent. So my 10th term is 115. My 5th term is 190. So I'm going to solve for 5D. So if I subtract 190, I get -75. And if I divide by 5, I end up getting D is equal to -15. Okay, now I can relate, now I can find any term that I want to find. Okay, so I want to find the 1st term. So I could use the 5th term or the 10th term to find it. I typically pick the one that's closer to it. So if I want to use the 5th term, I would say A subscript 5 is equal to A1 plus 4 common differences. Do you guys get that set up? It's always good to write it with A's and D's. So write the equation out with A's and D's. So the 5th term is 190. The 1st term is what we're trying to find. We know our common difference is -15. So I get 190 is equal to A1 minus 60. I add the 60 over. So I get A1. Make sense? All right, try the next one. So write an equation that relates the 2, find the common difference, then find the 50th term. All right, so we're going to relate the 2 that we were given. So we're given the 30th and the 41st. So I'm going to say if I start with the 30th and I want to get to the 41st term, how many common differences do I need? 11. So I have 11 common differences. So I have 25 plus 11D is equal to A sub 41, which is 3. We subtract the 25 over, we get -22 is equal to 11D. Did you guys all get D is equal to -2? Perfect. So now we go back and we want to find the 50th term. We can use any subscript we want. So let's say we use the 30th one that we were given. So we would need to add 20 common differences. So the 30th term is 25. We would need 20 times -2. So 25 minus 40 gives us -15. Did you guys get -15? I always kind of check and I'm like, okay, is it going in the right direction? So if I have 25 and I'm going to 3, like if I add on 11 swoops, it's getting smaller, right? 25, 3. So it makes sense that it would be negative if I'm even further out, right? So sometimes if people mess up with signs, they'll kind of catch that with that. All right, so do you guys remember the story I told you last year about a mathematician named Gauss? So mathematicians are interesting people. I went to grad school with a lot of mathematicians. Very, some of them are very Sheldon-like. I don't know if you guys know Sheldon Cooper. Very rule followers. But this guy, when he was, like, some stories have said he was 8, some have said he was 10. He got in trouble by his teacher. And she said, go to the corner and add up the numbers 1 through 100. And when you're done, you can come out of the corner. Okay, and so he went to the corner, and he started adding them together. And most, like, 8-year-old kids, I mean, if I asked my kid how to do this, he's 8. He would be like, 1 plus 2 is 3, plus 3 is 6, plus 4 is... I mean, it would take a really long time to add up those digits. Okay, so Gauss kind of thought about it. And then he was like, 5,050. And the teacher was like, there is no way that you're done with that. Go back to the corner and add up the digits 1 through 100. And he was like, yeah, well, what I did is I knew that 1 and 100 made 101. And I know that 2 and 99 make 101. And I know that 3 and 98 make 101, right? And there are 50 pairs of numbers. If I have 100 numbers, there's 50 pairs. So I have 50 pairs of 101, which is 50 times 100 plus 1. Right, so he said 50 times 100 is 5,000, and 50 times 1 is 50, so we end up getting 5,050. Right, so he knew right away. Isn't that crazy? Yeah. I don't know what his teacher said. I think I would be like, you're brilliant. Wow. You're allowed to do whatever you want to do from now on. No, so I don't know. So he grew up to be this brilliant mathematician, and his research led to a lot of things that we do in calculus today. So someone that studied under him, Riemann, ended up doing a lot of really cool things in calculus as well. So he was one of the most influential mathematicians of all time. Okay, so he came up with this sum of a finite sequence. So anytime I have this arithmetic sequence, meaning there's a common difference, see how this has a common difference of 1? I can use this trick because they're all evenly spaced, basically. So I can pair the first thing with the last thing and the second thing with the next to last thing. So what ends up happening is if I want to find the sum of n items, I find the number of pairs. So if I have n items, how many pairs do I have? Yeah, half of that, right? N over 2. So I have n over 2 is the number of pairs, and then I do my first term plus my last term. And really, it doesn't have to be the first plus the last. Like, I could have 2 terms that are in the middle, right, that are added together, as long as I know that they're the ones that are evenly spaced around that center number. And then the question is, does there have to be like a center number? If you have 100 terms, there's not something directly in the center, right? But if there was an odd number of terms, is it okay? Yeah, that number kind of gets like halved with itself. So if there was a number, like an odd number of numbers, the number that's in the very center is half of a pair, basically. Does that make sense? Okay, so it says find the 16th partial sum of the sequence. So we're like, oh, 16th partial sum, that's the sum of the first 16 items. So I'm going to have 16 divided by 2. That's going to be my number of pairs. And I'm going to have my first term plus my last term. So we start doing this, and we're like, okay, we got 8. We got the first term as 0. But then we have an issue because we don't know the 16th term. Do you see my dilemma? What do I do? Find the 16th term. Isn't that what we were just doing? So I find my common difference, which is 12. And I'm like, oh, if I want the 16th term, I can start with the first term and add on 15 common differences. So my 16th term is going to be 0 plus 15 times 12. So 15 times 12 is, I believe, 180. Yeah, 180. So then I go back, and I'm like, okay, I have my 16th term now. So I have 8 times 0 plus 180. So I end up getting 1440. And that's my answer. Make sense? All right, so the next one. So find the sum of all multiples of 6. If we start with 6 and we go to 606. So that's like 6 plus 12 plus 18 plus dot, 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 dot. 600, 606. That would be multiples of 6, right? So this time we do know the first and the last term. Do we know the number of terms, though? Yeah, not really. Okay, here's the trick. I think of 6 as being 1 times 6. I think of 12 as being 2 times 6, 3 times 6. This would be 100 times 6. This is 101 times 6. So how many terms do I have? 101. So I'm going to find the sum of the first 101 terms. And like I said, it's okay that we have an odd number of numbers, because that number in the very middle will be paired with itself. It's like half of a pair, basically. And so we're going to have the first term, which is 6, plus the last term, which is 606. So when I find this, I end up getting 30,906 is my answer. Okay, makes sense? Okay, so we're going to do geometric in a second, but I'll let you guys go on your break. All right, so we just talked about arithmetic sequences. So arithmetic sequences are when you're adding a common difference, like you're adding the same number every single time. So geometric sequence is when you're multiplying by the same number every single time. So a sequence in which consecutive terms have what we call a common ratio, so something that we're multiplying by. So in example 1, it says, is this geometric? If so, what's the common ratio? So see how we go 2, 4, 8, 16, and so on. Each time we're multiplying by 2, multiplying by 2, multiplying by 2. So because of this, this would be a geometric. And the common ratio would be 2, because it's what we're multiplying by. So maybe next to common geometric sequence, we say multiply by same number. So in this next one, do we think that it's a geometric? So what's happening with the numerator? Yeah, we're multiplying by like 1 on the top, and then on the bottom we're multiplying by 3. What about the positive, negative, positive, negative, positive, negative? So negative 1/3. So our R is negative 1/3. So yes, it is geometric. And we're multiplying by negative 1/3. Okay, so it's very similar the way we set up geometric sequences. They're very similar to the arithmetic. Okay. So how about these? So do you think natural log of 2, natural log of 4, natural log of 16, I know it has to be a step up from algebra 2 a little bit, right? Do you think this is a geometric sequence, arithmetic sequence, or neither? I don't know, let's see. So let's think about it like natural log of 2, natural log of 2 times 2, right? This would be the natural log of 2 times 2 times 2 times 2. There'd be 4 there. So I'm going to write this as natural log of 2 to the first, natural log of 2 squared, natural log of 2 to the fourth, like that. So do you guys remember that rule with logarithms? If you had like natural log of 5 to the 7, we can pull the 7 to the front. Let's do that. So we have 1 of the natural log of 2's. We have 2 of the natural log of 2's. We have 4 of the natural log of 2's. So are we multiplying by something every single time? Are we adding something every single time? Are we doing neither? Multiplying by what? 2. Yep, so we're multiplying by 2 each time. Right? Because I started with 1, and then the next one had a 2, and then the next one had a 4, and then it's going to have an 8, and then it's going to have a, and so on, right? So this is going to be a geometric. I guess I said find the 10th term. I got to make some room, huh? I didn't give you much room. So how do I find the 10th term? Yeah, so like this was, let's think about these numbers. This was 1, 2, 4, right? So each time I'm multiplying by 2, so if I start with my first term, and I want to get to the 10th term, I got to multiply by 2 how many times? To the 9th, right? So it ends up being 2 to the 9th times natural log of 2. That's going to be the 10th term. Whatever 2 to the 9th is. I don't know what 2 to the 9th is. So 512 times natural log of 2. Pretty big, right? All right. How about the next one? Geometric, arithmetic, neither. You guys hate the logarithms, don't you? You're like so uncomfortable right now. All right, do you guys remember the rule that says like log of A plus log of B is the log of A times B? Yeah. So let's look at these numbers. So we have 2, 6, 18, 54. How are those changing? Yeah, we're multiplying by 3, right? So what we're doing is we have log of 2. The next one ends up being log of 2 plus log of 3. And the next one ends up being log of 2 plus log of 3 plus log of 3. Do you guys see what I'm doing? Do you see how 2 times 2, or 2 times 3 times 3 is 18? Yeah, Greta?
How is this different from the last one? Because the last one was also
The last one was multiplying, like we were doing 1, 2, 4, 8, 16, right? Do you see how those are different?
Yeah.
Okay, this time we're gaining a plus 3, or plus log of 3, plus log of 3, plus log of 3. Okay, it's different. So is this one arithmetic or geometric? Arithmetic. Right, so it's arithmetic because we're gaining a d of log of 3. So if I was finding the 10th term, I would start with my first term, which is log of 2, and I would add on 9 of those common differences. What do you think when I say 9 of the log of 3's? Do you guys remember how we were talking about that? Log 3 to the 9th, like that. That's like a 9 out front. We can pull it up as a power. You know what I'm saying? So we're going to do 3 to the 9th. So 3 to the 9th is 19683. And then we're going to do, we have log of 2 plus log of 19683. So what do we have to do? We're going to add those two, or we're going to multiply by 2. So this answer, the 10th term, is log of 39366. So 39366. Okay. Now don't feel like this is the only way that you can get that. If you want to just look at the individual numbers like that you're taking the log of, if you look at 2, 6, 18, 54, and so on, that is a geometric sequence, right? So if you wanted to find like the 10th term of that, and then just do log of that, you could do it that way as well, okay? So in many ways, like with logarithms, the arithmetic and geometric thing are kind of interconnected, right? Okay, so let's try this next one. So it says the nth term of a geometric sequence is always we start with the first term and we multiply by our r, our common ratio, n minus 1 times. Okay, again, don't memorize it, just know how to get from one term to another. So if I have the 5th term and I want to get to the 12th term, I multiply by r 7 times. Okay, so it says find the common ratio of the geometric sequence with a sub 7 is equal to 3 and a sub 9 is equal to 12. So I'm going to write an equation that relates the 7th term to the 9th term. So how many times do I need to multiply by r? 2 times, right? To go from 7 to 9, so 2 times. So I have 12 is equal to 3r squared. Divide by 3, I get 4 is equal to r squared. So r is equal to actually plus or minus 2. So that's where this question comes into play. So it says, question, could there be more than one sequence? Yeah, actually it could be an alternating sequence, meaning it could go positive, negative, positive, negative, positive, negative, right? Or it could be one where we just have r is equal to 2 and they're all positive. Okay, so there could be more than one. So list the first 5 terms of the sequence. So we got to figure out what the first term is in order to do that, right? So let's go back and let's find the first term. Well, if I'm trying to get to, let's say, the 7th term, I would need to multiply by r 6 times. So So I have 3 is equal to a1 times plus or minus 2 to the 6th. So if I have positive 2 to the 6th, I get 64. If I have negative 2 to the 6th, you see how I also get 64. So this is 64. So a1 is the lovely number, 3 over 64. So if I'm listing the first 5 terms, I'm going to start with a1, which is 3 over 64. And then I'm going to multiply by 2. When I multiply by 2, what's my denominator become? It's still 3 over something. 3 over 32. And then 3 over 16. And then 3 over 8. And then 3 over 4. That's one possible sequence. But we could also have negative 32, right? So I could have plus or minus there and plus or minus there. Not on all of them, just on the every even number term. Make sense? Okay. Tricky? All right, so let's try some more. It's a long section, I know. So write the explicit form of a geometric sequence where the first 2 terms are 3 and negative 3/4. So if I have 3 and negative 3/4. So I know it's a geometric sequence, so I need to figure out what r is. Whenever you're trying to find r, you can take any term and divide by the term before it. Right? So I can set up the equation with a1 and a2. So if I set that up, a1 times r to the first is equal to a2. Do you see how I would have my a2? And I would have to divide by 3 in order to get r. That's what we're doing. We're saying take the second term and divide by the first term to get r. So if I do negative 3/4 divided by 3, I get negative 3/4 times 1/3, which is negative 1/4. Could you guys do that without writing that whole thing? Probably. You could think of it as like 3 over 1 and say, oh, I need a negative 1 on top and I need a 4 on the bottom. Yeah? So I get r is equal to negative 1/4. So find the first 5 terms of the sequence. So we're going to have 3, negative 3/4. What do I get when I multiply by another negative 1/4? Positive 3 over, and then I get negative 3 over, and then I get positive 3 over, a little bit harder. So 64 times 4. You can double and double again. So 256. And that's the first 5 terms. All right, try number 4. So write an equation that relates the 4th to the 7th term. I don't know why it's number 4. It should be number 3, shouldn't it? But write an equation that relates the 4th and the 7th terms. And then I want you to find the 6th term. All right, so the 4th term and 7th term. So we're going to set it up and we're going to say, if I want to start with the 4th term and get to the 7th, I need to multiply by r how many times? Nope. You keep doing one less, don't you? Yep, 3. So it's going to be a sub 7 equals a sub 4 r cubed. Are you thinking of like the n minus 1 thing? Is that what you're thinking? So if you want like the 10th term and you start with the first term, the reason it's 9 is because these numbers add up to be 10, right? Because we're starting with term 1 and going to 10. Does that make sense? Yeah. All right, so we're going to have that. So my 7th term is going to be 2/3. My 4th term is negative 18. And then I get r cubed. Okay, so it gets a little messy for a second. I think we can handle it. So we're going to take that, we're going to take the 2/3 and we're going to divide by negative 18, which is 2/3 times 1 over negative 18. So I get 2 over negative 54, which reduces. It becomes negative 1 over 27. Did you guys have that somewhere? So what did you get when you took the cube root? Yeah. So the cube root of negative 1 over 27. Take the cube root of the top and the cube root of the bottom. So the cube root of negative 1 is negative 1. What's the cube root of the cube root of positive 27? 3. So it's negative 1/3. Make sense? So now if we want the 6th term, we say, oh, the 6th term is just going to be my 4th term multiplied by r twice. Or I could set it up with the 6th and the 7th term. It doesn't matter. I could say the 7th term is equal to my 6th term multiplied by r once. So my 6th term is going to be a sub 4, which is negative 18, times this negative 1/3 squared. What's negative 1/3 times itself? Put that calculator away, Ben Westerkamp. 1 over 9. So what's negative 18 times 1 over 9? Oh my gosh, all of you putting this in your calculator. Negative 2, you got this. Without a calculator, amazing. That would be a great non-calculator question. I should ask something like that. The cube root of 27, just knowing that would be amazing. If you just could just know. All right, so the sum of a finite geometric sequence. So this is a little tricky. So if you have a finite sequence, you can add things up and not get infinity, right? So if you have a certain, if I have 100 numbers, if I add them together, I'm not going to get infinity, right? But if I have an infinite sequence, I might get infinity, right? Let's think about sequences that would add up to be like infinity. What if I had 1, 2, 4, 8, like that geometric sequence? And I had an infinite number of terms. You guys see how it keeps getting bigger and bigger and bigger and bigger and bigger. If I have an infinite number of terms, it's going to be infinity. But if I stop after the 50th term, it's not going to be infinity. It's going to be a really huge number, but it's not going to be infinity, right? Does it make sense? Okay, so the question is, if I have an infinite number of terms, won't it always be infinity? I don't know. Is it? So what if you have a sequence that looks like 1, 1/2, 1/4, 1/8? Do you guys remember talking about this before? Can I add up all of those terms in the sequence? And if I add up an infinite number of numbers, do I get infinity? I don't know. So the sketch on this, I do know. The sketch on this looks like this. It would be, I add 1, right? That's filling in the space 0 to 1. If I add 1/2, I'm filling in here to here. 1/4, I'm filling in more, right? 1/8, 1 over 16, what does it eventually become? 2. It's 1.99999 repeating, which actually is the number 2. Have I taught you that proof on why 0.9 repeating is actually equal to 1? I'll do that. That's pretty fun. I won't do it right now, but too much. It just blows your mind. All right, so this is a finite sequence that we have. Okay, there's not an infinite number of terms. How do I know? Because it doesn't say ... at the end. Okay. How many numbers do I have? Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 numbers. So I'm going to find the sum of the first 9 terms. Okay. I'm not going to bore you with telling you where this formula comes from. I'm going to give you this formula on your test. So you're going to have A1 times 1 minus r to the 9th all over 1 minus r. So we're going to have A1 is negative 5 over 2. What's our r value? Yeah, it's negative 1/2. So I'm going to put that negative 1/2 in parentheses. So always put r in parentheses. I think that will help you out. So it's like that. Okay. We're going to let our calculators do the work. Are we ready for this? Get your calculator out. The first thing I always tell students to find is the denominator. So if you do 1 minus a negative 1/2, that's 1 plus 1/2, that ends up being 1.5, right? Or 3 over 2 if you want to write it that way. So let's write it as 1.5. All right. So think about your order of operations. Parentheses, exponents, multiplication, division, blah, blah, blah. So we're inside these parentheses. We have to do the exponents first. So I want you to do parentheses, negative 1/2, and I want you to raise it to the 9. So you have negative 0.00195, blah, blah, blah. All right, next step, what are we going to do? 1 minus answer. So 1 minus answer. So I get 1.00195, blah, blah, blah. Now what? Times negative 5 over 2. Divided by 1.5. Okay, so I had negative 2.50488. So I ended up getting negative 1.6699. Okay, that seems weird that it's negative. Is it okay that it's negative? Yeah, because the biggest thing was that first number. It was negative, right? So negative 5 over 2 is like negative 2.5. If I'm adding 1.25, I'm not filling that negative spot, right? So it's still negative. All right. So an infinite series. So what I want you guys to do on your calculator is I want you to take the number, so put in parentheses 1/2. So 1/2 is smaller than 1, right? If I found the sum, well, not the sum, but if I found 1/2 to the 9, right? It's pretty small, 0.0019, whatever. What if I do 1/2 to the 50? What's your calculator tell you? Yeah, it's 8.88 times 10 to the negative 16. That's like 0.0000, lots of zeros, right? What if I do 1/2 to the 100? What does your calculator tell you? Even smaller. What about 1/2 to the 500? What does your calculator tell you when you do 1/2 to the 500? It tells you 0. Is it actually 0? No, it's 1/2 to the 500, right? So it's not actually 0, but your calculator can't handle how close to 0 it is, and it makes it 0. So this formula that we just did, do you notice how it has this r to the n? If r is a number less than 1, when you do r to a really huge number, like almost infinity, it will be infinity. If you do a small number raised to a huge number, that goes away, okay? So the sum of the geometric sequence ends up being a1 over 1 minus r. It's like that part that was 1 minus r to the n became 1 minus 0. It went away. Okay, so it's part of that formula. Okay? I don't know if I'll give you that one or not. I think you can know that one. Actually, you get a no card anyway, so you can write it. All right, so compute the following infinite sums. So if I have 1/2 plus 1/4 plus 1/8 plus blah, 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 that's what this is saying, okay? So if I plug in n is equal to 0, actually it's saying, what happens if I plug in n is equal to 0 here? What's 1/2 to the 0? 1. So it's actually saying 1 plus 1/2 to the 1 is 1/2, plus 1/2 to the second is 1/4. And it's saying forever. That's the one that I just said. I said it was equal to 2. Let's use the formula. So we're going to use this a1 over 1 minus r. So a1 is 1. 1 minus, what's r? 1/2. So I get 1 over 1/2. A1 is this term right here, the first term. So 1 divided by 1/2 is 1 times 2 over 1. So we end up getting 2. Okay, how about the next one? So we could plug in 0. If I plug in 0, I get that part's 1, so 2 times 1 is 2. What if I plug in 1? Negative 4 over 3. The next one ends up being plus 8 over 9 plus dot, dot, dot. So it's a geometric sequence. Can you guys see what r is? Close. Negative 2/3. Okay, it's this number right here. Was it this number right here before? Yeah. Why does that make sense? Each time you're gaining another r value, right? As I plug in 1, as I plug in 2, 3, 4, 5, I'm gaining another times whatever this r value is, right? That's why it's a geometric sequence with that r. So I'm going to have the sum, let me write s is equal to, sum of infinite we just write as s. We don't do like a subscript. So s is equal to a1 over 1 minus r. So a1 is 2, 1 minus a negative 2/3 is 2 over 1 plus 2/3, which is 2 over 5/3. When you flip it, so 3/5 times 2, you end up getting 6/5. Yeah, you see it. All right, does this make sense? All right, we can skip the last one, it's fine. All right, so let me pass out your homework.